Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Triangulation is brought to you by CacheFly at CACHEFLY.com. This is Triangulation, episode 319, recorded August 14th for airing October 27th, 2017. Our friend, gallium nitride. Triangulation is brought to you by Rocket Mortgage from Quicken Loans. Home plays a big role in your life. That's why Quicken Loans created Rocket Mortgage. It lets you apply simply and understand the entire mortgage process fully so you can be confident you're getting the right mortgage for you. Get started at rocketmortgage.com/triangulation. And by ZipRecruiter. Are you looking to hire a tech professional? With ZipRecruiter, you can post to 100-plus job boards, including social networks, all with a single click. Screen, rate, and hire the right candidates fast. Try ZipRecruiter free at ZipRecruiter.com/twit. It's time for Triangulation, the show where we get together with some of the most interesting people in technology, get to pick their brains for an hour. And this is going to put your, as Steve Gibson says, put your propeller hats on for this one, because we're going to talk about semiconductor technology. Alex, now let me say it right. Lito?
Correct.
Is here. Alex, welcome. It's great to have you.
Thanks so much, Leo.
Alex is the co-inventor of the HEXFET Power MOSFET. Okay, right? Now, how do you feel? He's also an author of the book Gallium Nitride Transistors for Efficient Power Conversion. Former CEO of the aptly named International Rectifier. Good name for a company. I like it. Well, everybody knows what a rectifier is. So
sounds like a medical procedure.
It's either that or maybe like a Marvel superhero. I'm the rectifier. But he's currently CEO and co-founder of a company called Efficient Power Conversion. Alex, welcome to Triangulation.
Thanks,
it's great
Leo.
to have you. Was it your PhD thesis, your senior thesis? You wrote about this new technology, gallium arsenide?
Yeah, it was my PhD thesis at Stanford, right. I thought it would replace silicon. It was the next best thing.
So I'm going to ask you to explain, how do processors get made? No, well, kind of.
Yeah.
Kind of. And it's my understanding, and you're going to correct me, and I have a very rudimentary understanding of this, that of course, in the old days, and there are still people doing this, you had tubes, you had valves, you had complicated but physical circuitry to build an electronic circuit. And to build a computer, you had a bunch of tubes, right, in the earliest days. But once the transistor came along, we were able to reduce these technologies to chips and then to microprocessors, which were as if you had millions of transistors on a chip this size. How do you do such a thing? Well, you're reducing it, dramatically reducing it. So a chip designer would design a chip with all the circuitry needed to make a microprocessor. Then they would reduce it, make a silk screen of it, in effect, right?
Yeah, they used to be called rubyliths, and they were hand-cut red and white representations of what you wanted to print on a tiny little chip. I used to sit there on a light table for hours cutting these things with a razor blade.
You actually did that?
Oh, yes, absolutely.
Holy cow! And then
comes with the gray hair.
and then this stencil, in effect, right?
Yeah.
Would be placed on what's called a semiconductor, kind of a silicon substrate that didn't conduct very well.
Right.
And you would dope the semiconductor with something that would make it conductive through the slits that you had cut there. That would make traces and, in effect, put circuitry on the semiconductor.
Exactly, yes.
Yeah.
That was Jack Kilby and Bob Noyce that figured that out independently. And then over time, we got better at the photography part of it, and we're able to make it smaller and smaller and smaller and smaller.
That's how these chips have gotten more and more powerful.
Yeah, so now actually I think some of those Intel chips have 3 billion transistors on them.
It's amazing, isn't it?
Yeah.
And of course, we're I think probably pretty close to the end of Moore's law. Gordon Moore, very wisely 40 years ago, maybe now 50 years ago, intuited that because of this and the ability to reduce the size of these components, we would be able to double the number of transistors on a chip every 18 months. And in fact, that came out to be true.
Yeah, it's pretty close, but I think that Moore's law was a social compact more than it was a technology story.
He said, we'll do this, as opposed to this is what's going to happen.
But there was an implied thing there that as we increase the number of transistors on a chip, that we will get more functionality at lower cost.
Right.
And that happened year after year after year. And after enough of these cycles, all of the users of these fabulous integrated circuits started realizing that this was going to continue. So they started coordinating their developments to it. And as Moore's law has run out, and in fact that social compact was broken about 5 years ago, where it started becoming, more functionality or lower cost, instead of and so now you've actually seen a slowdown because people don't want to coordinate their developments with an expectation of Moore's law.
Expecting a plateau, they've plateaued the software.
Now they say, I'll work on software, or when that new chip comes out, then we'll see what it does, and then I'll start my development around it. So you've seen this century a tremendous slowing down of the end markets.
I think all the people watching know that, because really, truthfully, the computer you bought 5 years ago wasn't significantly slower than the computer you buy today.
That's true. And the software has sort of become more bloatware, so it kind of slows it down in compensation.
Well, for a while, we were, though, in this very painful cycle where processors would get faster, so Bill Gates and Microsoft would put more capability in their operating system, and people would, Norton would bloat up its software, and then it got slow again, and then the processor would get faster. And there was this cycle, but that cycle is kind of, if it hasn't come to the end, it's close to the end of this cycle.
Yeah, and you can still say that there's more technology development to be done in silicon, but it is more of that or rather than the and. That it's coming at a price that doesn't get paid for by the at the same time as the performance.
Well, we look what's happening in silicon. First of all, Intel's struggling, which is a shock because they've drove this for so long, partly because ARM has come along with a kind of a different technology that's lower power, lower speed, but lower power. Intel's struggled to provide chips, lower power chips that are CISC chips versus RISC chips. Then we've got this issue of Intel thinking it could do a chip that would be faster than 4 gigahertz. That's turned out to be very difficult to do. So they did multiple processors instead of a single chip. They did parallel processing instead of getting faster and faster single processors. The road has gotten bumpy.
Yeah, but I think that you can see tremendous innovation. There's multi-core processors to keep things going and stuff like that. As the fundamental Moore's law gets slowed down there, and now I think it's pretty much near its end in terms of being able to cost effectively improve the chips very much.
So back when you were writing about gallium arsenide technology, I said arsenic when I first met it. And that's not arsenic, although it's related, right?
That's the other component. It's gallium and arsenic.
And arsenic, it is, okay. Yeah. What were you what was the purpose of that? And what was it to replace?
So I went to graduate school in the mid-'70s, and I thought, well, silicon's been around 20 years.
That was the semiconductor substrate, the non-conductor
silicon substrates. There was 3 years since Intel introduced the 8008. I thought, this is end of the road, man. Got to come up with something new. So I went into gallium arsenide thinking that would be the replacement
instead of silicon.
Instead of silicon, this is gonna revolutionize.
And why
the
is
whole
it
thing.
better than silicon?
So gallium arsenide is a whole lot faster than silicon. Silicon is a wonderful material for a million reasons.
Well, wait a minute, faster? I thought this was a non-conductor.
Well, the speed of electrons when you allow it to conduct. See,
I see. By doping it, you're allowing it to conduct.
Yeah, by adding impurities, you actually create paths for electrons or positive charges called holes to go around.
So that's impacted by the choice of the semiconductor.
Yeah, absolutely. And so gallium arsenide just was a whole lot faster, and so you could make things smaller, faster, better.
Right.
Except it had some fundamental disadvantages.
I thought it was the speed of light. How could it be faster than the speed of light?
Well, the electrons actually don't go faster than the speed of light in a semiconductor. They have what's called a saturation velocity.
So they're a little slower.
They're a little slower because they're banging around off of pieces of crystal and things like that.
So with less banging around, you have faster electrons?
With less banging around, or with a crystal that, for example, is just more slippery inside.
Yeah. Interesting.
Yeah. And now with gallium nitride, we have a whole different principle, which we can get into.
So we're using, instead of arsenic, nitrogen and gallium to create, again, a semiconducting substrate that you then modify, you dope to make it conductive.
Actually, you don't even do that.
You don't
anymore.
even dope it anymore.
No.
Well, I have a lot to learn. I have a lot to learn. Well, we're going to take a break. When we come back, we're going to talk about it. And a little later on in the show, you have brought product. This is not kind of airy-fairy. This is in many of the products you're using today. We're going to show you some of the things that you're using gallium nitride.
Yeah, stuff that wasn't around with silicon in the silicon age because it couldn't be done. It wasn't fast enough.
Wow. And your company, Efficient Power Conversion, makes about 80% of these.
Yes.
What are they? Chips? Do we call them chips?
They're either transistors or integrated circuits. We make both.
ICs or FETs, FETs, field effect transistors.
Exactly.
Yeah. Okay, I'm learning a lot. I hope you are too. We'll have more in just a second with our guest, Alex Lidow. We're going to have more with Alex Lidow and our friend Gallium Nitride in just a little bit. Our show today brought to you by Rocket Mortgage from Quicken Loans. I have to say, first of all, let's just say it. Quicken Loans is the best mortgage lender in the country. Not the biggest. They're number 2. The biggest you don't want to go to. That's who Lisa and I borrowed from for our house that we bought 4 years ago. Big bank. You know them well. What a pain in the tuchus. It was a nightmare. First of all, you have to go somewhere, right, to get the loan. You have to go to the bank or the loan office, and then, you know, you give them all this information. You fill out this long form. Then you go home. And in a few days, they say, okay, we need this, and this, you know, pay stubs or bank statements. We sent them all that. We brought it in, I think. Good. Oh, we should get the loan any day now, right? No. Weeks go by. They ask for more stuff. We send them more stuff. More weeks go by. We're thinking, in fact, the guy selling us the house said, are you getting the loan? Because I'm going to sell it to somebody else if you don't hurry up. We said, well, yeah, we're getting the loan. We're going on vacation next week. We better get the loan. We go on vacation, still no loan. Finally, we're faxing stuff from vacation. We're calling Lisa's sister, Debbie, and saying, could you send them? It was a nightmare. We finally got the house, thank goodness. But I have to say, next time it's Rocket Mortgage, please, Rocket Mortgage. Quicken Loans, #1 in customer satisfaction, J.D. Power customer satisfaction, 7 years running for primary mortgage origination, 4 years running for mortgage servicing. They're really a great company. And they got a place in my heart because they did something for us geeks. They created a completely online loan approval process. No more going to the bank or the loan office. No more lugging in boxes of papers. No more going to the attic. You don't even have to give them papers. You go online right now. You could do it in minutes. Rocketmortgage.com/triangulation. You give them the basic information they need. They have trusted partnerships with all the financial institutions. So they say, is this you? Okay, do we have permission to access this and this and this? And you say, yes. Boom. That's it. That's it. They start crunching the numbers, and it's computers, so it's fast. And based on your income, assets, and credit, Rocket Mortgage will analyze all the home loan options available to find one that's just right for you. You get to pick the down payment, the term, the rate, all of that. It's all completely transparent. It couldn't be simpler. And then, not in months or weeks or days or even hours, but in minutes, literally, while you're there looking at the phone, you're approved. That's it. You're done. You could do it in an open house. And while the realtor's showing the other couple the house, you could say, hey, by the way, we're approved. See? Show them your phone. You're approved. I can't tell you what an advantage that is if you're trying to buy a house these days, because it really is a seller's market, and the competition is fierce among buyers. And if you could say, no, I got the loan, you're golden. You're golden. Get started at rocketmortgage.com/triangulation. Equal housing lender, licensed in all 50 states, NMLSconsumeraccess.org, number 3030. Apply simply, understand fully, and then mortgage confidently with Rocket Mortgage from Quicken Loans. Go to rocketmortgage.com/triangulation. We thank Quicken Loans for their support of Triangulation. Now back to gallium nitride. Welcome back to Triangulation. Alex Lidow is our guest. He is the founder and CEO of a company called EPC, or Efficient Power Conversion, and an expert in gallium nitride technology. GA for gallium, N for nitride.
Correct.
Technology.
Yeah.
As we talked about earlier, this is the semiconductor that replaces silicon in a whole class of new ICs and transistors.
Right.
So when did we start using? I remember I've read about all this. I remember when we reading about gallium arsenide, and at the time, many years ago, it was the great hope.
Right.
Why wasn't it the great hope?
It turns out it was expensive. Expensive to
Silicon's cheap.
manufacture.
It's sand.
Silicon is cheap,
Yeah.
and also very robust in processing. It's easy. It's not easy to manufacture, but it's robust in manufacturing.
So you have to when Intel or any chip manufacturer makes a chip, they make a giant thing with
They're
a lot
this
of
big now. They're this big.
big. What do you call that?
A wafer.
Wafer. Oh yeah, wafer fab.
Uh-huh.
Big wafer, and it has many processors on
Yeah.
it because they've just doped a giant wafer. But the issue is are all these processors good? How pure is the substrate?
Yeah.
How easy was it to make? And you've seen the bunny suit ads and everything. This is a hard thing to do.
And when you have gallium arsenide, when you heat it up to even a few hundred degrees centigrade, the arsenic starts boiling off, which it's not a good thing. So
You need more than a bunny suit. You need a hazmat suit.
So it's a little unstable,
Yeah.
but people have mastered it for certain very high performance things.
So it is being used.
It is being used. It's maybe a $2 billion a year industry in things like some cell phones use it, but not many anymore.
Okay.
But it's used for very high frequency data transmission and very high frequency radio transmissions.
More in the radio chips.
Yeah.
Yeah.
But I think that its age is coming to a close.
When did nitride become the chemical of choice? Nitrogen.
About 1999, some researchers in Japan figured out how to grow gallium nitride as a very thin layer on top of a piece of standard silicon.
Oh, interesting.
And that really turned on the light bulb for me because it took gallium nitride was robust. I knew that from
Yeah.
my chemistry.
Right.
And it was expensive to grow as a crystal, like you do silicon, a solid crystal.
Right.
So it had a cost problem. But if you could make a layer that was, say, a millionth of a meter thick, a micron thick on top of silicon, and then make your devices in that, you solve the cost problem, but you get the performance advantage.
Interesting. Because it's really still the gallium nitride where all the electrons are traveling. They're in
Exactly,
that layer.
yeah. And gallium nitride has a property that is actually, it's fairly rare, in that you can make electrons move extraordinarily efficiently because they actually go into a quantum mechanical state. It's very different
No
than in
kidding.
silicon, yeah. So you squeeze the electrons into a quantum mechanical state right at this one interface between two materials, and then they go like greased lightning wherever you want them to go.
Well, can't they just go from point A to point B without being anywhere in between, or am I confusing quantum mechanics? And
Well, you create it's called a two-dimensional electron gas,
yeah,
and you confine that gas to where you want it to be.
yeah.
So within that gas, the electrons are extremely efficient.
Wow, you're greasing the tube.
Right. So
Yeah.
gallium nitride starts off being a better material because it has a stronger bond between the gallium and the nitrogen. So that means that it can withstand more electric field.
Right.
And electric field means you can make the device smaller.
Interesting. Okay.
So theoretically, if you want to conduct power, you can make the devices 6,000 times smaller than silicon.
We're in silicon. We're doing 15 nanometer processes now,
Yeah.
right? That's the smallest one I think that's currently being used. Can you go below 15 nanometer?
Yeah, actually, there are even 10 nanometer devices
No
coming out
kidding.
right now. Yeah, and then going to 7 and then even 4.
And so gallium nitride lets you go down to these.
You can go down to any of those levels, but we're not there right now because we're working on conducting power and on analog, and then we'll go to digital.
Yeah.
The minute you go to digital, it's kind of a whole different level of investment and some technology challenges.
We've seen fab costs go through the roof.
Skyrocket,
I remember
yeah.
it was $1 billion to build a fab. I think it's like 10
Right.
billion now to build.
Yeah, that's a
chip
starter
fabricator.
kit.
That's a little fab, a baby fab. Wow. So it's fascinating to watch this, and I think most people who use technology, they're oblivious to this. Is it faster? Yeah. Why? I don't know, and I don't really care. I think our audience, I think I'm not giving you too much credit when I say are very interested in the kind of the underpinnings of this,
Right.
and it's fairly important because if you understand these technologies and how they're changing, you kind of can get a little crystal ball into
Right.
what's going to happen in the future. So, did the Japanese scientists who invented gallium nitride, do they own that? Is it
No.
patented?
Well, there are lots of patents floating around, but you can weave through them. It's still a pretty open field.
Interesting.
Yeah, and I don't think there's any litigation going on in that area in patents.
So
at
when
this
you
point.
started EPC, you started it with the idea of what?
So start with the idea that I can make something much higher performance than silicon and much lower cost. That was our thesis.
That's pretty good.
And I figured I could do better than an order of magnitude on each.
That's trumping Moore's law in
Right.
effect.
I think today we're already 100 to 1,000 times faster than silicon, and we're already cheaper than silicon.
Wow. Now, when you okay, that's that's more than an order of magnitude.
It's the first time
That's
ever.
significant. So when you say faster, we're not talking clock speed. I know when we talk about processors, we're talking about gigahertz clock speed. It's not clock speed.
It could be that, but we're actually talking about things like how fast you can transition from a 0 to a 1. Or in the world of power, how fast you can transition from power on to power off.
Interesting.
And that can be very, very critical to things that weren't possible with silicon before.
Well, if you think about it, RAM, memory, the speed of the memory is really determined by how quickly you can
Right.
set a 1
Yeah.
or turn it off.
Right.
So it would speed up RAM by, what did you say, 100?
Yeah, I think that
1,000 times?
if you were to create it in the same line widths and things like that, there'd probably be a 10 to 100x improvement in
Holy
speed.
cow.
There's something called the Johnson limit, which is the limitation of the combination of speed and voltage, and,
Right.
and it's about
Right.
10 times higher.
Still,
Yeah.
that is an order of magnitude. That's a significant
Yeah.
improvement.
But when you're doing things like analog functions or power
power,
functions, you
yeah.
get even a bigger multiplier.
So that's why you chose power.
I chose power because that's the industry I came in. So I'm
Right.
like the drunk looking for my wallet under the lamppost.
I know where it is. Right here.
I lost it over there, but this
Power.
is where the light is.
So this is interesting. So why would being able to switch it on and off faster be useful in power?
So when you think about power, you're converting from one state of energy to another. And the way it works is you take this state of energy and you chop it up into small packets of energy, and then you reassemble it at the final state. It's called switching power conversion.
Okay.
So
I've heard switching power supplies.
Right.
That's what we're talking
yeah,
about.
and those switching power supplies were enabled by the component that we talked about earlier, the HEXFET power MOSFET,
Right.
that my colleague and I invented back in 1978.
Okay. Now, by the way, as soon as you get analog, I'm a dummy. I think I understand digital a little better, but analog is a little bit, for me, well, tough. So you're going to have to talk baby talk here for me, just a little, just a little bit. So, is it related to AC versus DC? This switching?
Well, really, most everything is DC to DC.
Yeah,
'Cause
that's why we have a
AC
transformer. We have that big brick. You plug it into the AC, but
Right.
it converts it to DC for your laptop or whatever you're
Sure,
charging.
basically everything
Wants
goes
DC.
DC except for motors.
So
They
what
like
does a
AC
switching
sometimes.
power supply do then?
So it takes in AC from
Yep.
your wall socket,
Yep.
and it immediately converts it to DC.
Okay.
And then there's a DC to DC converter that converts it from where it comes in from the
It
wall.
steps it down.
A couple of hundred volts, and
Yeah.
steps it down to 12 volts or
Right.
1 volt or whatever you want.
Right.
And it does it by chopping that initial flood of electrons up into small energy packets, and then they get reassembled on the other side at a lower voltage.
So that's where the switching is happening.
Yeah. And
It's part of the step down and transformer.
Right.
To reduce voltage.
And so the faster you switch, the smaller all the components are
Right.
that are needed to handle that little packet of energy. So as you go to higher frequencies, the packets get smaller and the system gets smaller and lower cost.
And lower heat, which is a big issue, of course. Yeah.
Now, the downside of this whole thing is it takes energy to switch. And in silicon, it takes 10 to 100 times more energy to switch than in gallium nitride.
Right.
So as you go to higher frequencies, you waste more of the energy just switching from the on to the off state.
Is that translated to heat? What is that translated
It's translated directly into heat,
Yeah.
and that's translated into, that's wasted energy.
to? Right.
So when you come up with something like gallium nitride, and this was the original thought of the whole business, you can make these power supplies at much higher frequencies and therefore much smaller and much cheaper.
But aren't you going to have this efficiency issue?
The efficiency is related to how efficiently you can switch from 0 to 1.
Oh.
And gallium nitride, it's a whole lot
Solves
more
it.
efficient. Yeah.
Solves
So
it.
all of a sudden, all these new power supplies were possible, but out of the woodwork came all these other new things that needed power but required frequencies much higher than silicon could handle. And those became our early adopters, the crossing the chasm, the valley of death.
Right.
Those are the people we're holding on to, dragging us through the valley
You
of
need
death.
those, though, because you can't jumpstart the business unless you have
Absolutely.
these early adopters. So what are the first technologies that are going to use this gallium nitride?
Well, they're already out there. There's millions of these devices out there today.
You
and-
probably own one right now. I'm looking at. We're going to do a demo in a second. I own several of these.
Yeah,
Right.
probably so.
Yeah.
But one of the earliest ones was this wonderful company, and that has this wonderful inventor as the founder and CEO, came to us and said, we'd really like to use your devices because they're very fast, and they would make our LiDAR system higher resolution. And higher resolution is important because LiDAR is not quite as good as radar. But with your gallium nitride, it could be much, much better than radar.
Higher resolution,
Higher
better
resolution.
imaging means
At
better
lower
self-driving
power.
cars.
And with less processing required. So the company was Velodyne.
Oh,
And
okay.
and
I think
so,
I've heard of them.
Yeah, many people have heard of them because Dave Hall, who's a brilliant inventor, started out making speakers,
Right.
Velodyne
Right.
acoustic, right?
Yep.
And so he tinkered with LiDAR and made that ARPA challenge car with LiDAR, but the resolution wasn't good enough. And not only that, but because silicon's so slow, it gives you a fuzzy kind of resolution,
yeah.
and it takes a long time to paint
Yeah,
a picture.
yeah.
With
So the
gallium
car
nitride-
drove off the road the first time.
or it's a big rock or something. I don't know.
Yeah.
But with our stuff, you can paint really fast pictures.
We actually have some images, some LiDAR images.
Yeah, I think
from
you got one
from
rolling
a
here, or
Velodyne,
we'll have it
this
rolling
is
here.
from a Velodyne LiDAR.
Yeah.
This is the king of the hill in terms of self-driving cars. Everybody, except for, which is interesting, Uber, and because they stole it from Waymo, from Google, Waymo invented a less expensive form of LiDAR. They're about 1/10 the cost of Velodyne's products.
So, I use this expression. I don't know if you heard it before. First liar doesn't have a chance. So, Velodyne produces an enormous number of LiDAR systems, and then along comes another company and say, but I can do it for 10 times
Right.
less. Just wait and see. It'll be out in a couple of years.
Hasn't
And the
happened
next
yet,
one
huh?
says, I can do it even less than
Yeah,
then. Wait
yeah,
and see. You'll see it in
right.
3 years. So, it has been talked down from, a few $1,000 system
Right.
down to where people are claiming that they can do it for $50.
Right. That would
and-
be a breakthrough, obviously.
and it would be, and it will happen.
Yeah.
I worked on some of the very first anti-lock brakes in the late 70s through the early 80s with General Motors. And at first, they cost $2,000 a
No,
wheel.
it was. Everybody said you should get one, but
Yeah.
it's too. You're not going to have it.
Well, but
Now
the-
every car has it.
Not only that, but commercial aircraft bought it right away.
Yeah, because that's a pittance compared to the cost of a
Right.
jet.
They didn't care. $2,000
Right.
a wheel, that's
Big
cheap.
deal. Yeah.
Then big rig trucks
Oh,
bought
interesting.
it.
Yeah.
And then high-end Cadillacs offered
That's
as an
right.
option.
It's a big
now
deal.
it's $5 a wheel.
Right.
So when somebody says, "Oh, that LiDAR, that's so expensive," I just think back, wow, I did that with anti-lock brakes. We did that
Interesting.
with airbags.
Yep.
Where it was $2,000 for an airbag. Now they're a few dollars, and they're
Right.
everywhere in the
Isn't
car.
that interesting?
So you can see how these costs get driven down, and
Yeah.
LiDAR's no different than
Do you
that.
have, Carsten? I think it's in the DDR. The image of or is that actually going to be the image from that LiDAR?
Yeah, we'll
Wait,
see.
what, we have a live LiDAR picture of the studio?
Yeah,
Well,
stand back.
I don't know if I really want. I don't know if I really want that.
No, it's great. We'll go autonomous.
How
now.
does LiDAR work? Is it like radar where it's bouncing signals off of all the solid objects, or?
It's even better than radar because radar uses electromagnetic waves to
Yeah.
bounce off of things.
Microwaves, in effect.
Yeah, microwaves, millimeter waves,
Yeah.
and they bounce off and they come back. But they come back because it's a millimeter wave and it's non-directional. You get a fuzzy image, basically. And so a radar system has to be supplemented with a camera or a series of cameras in order to figure out what's going on. There you go.
Wait a minute. If I wave, is it going to? Oh, it does. It sees I'm over in the lower right-hand corner
Yeah,
waving.
we're both over here.
Oh, wow.
Yeah.
Well, that's really cool. And of course, getting the cost down on these things puts it in more than just Teslas or self-driving test vehicles. It puts it in a Roomba vacuum cleaner. It puts it in
Exactly.
all
or
over the house.
augmented reality glasses, which will
very
also
important.
use LiDAR.
Very key. Right.
And drones,
Yep.
they're using LiDAR as well. So
Look at that. That's amazing. That is so cool.
So it can paint this image.
It's fast.
Almost
It's fast
instantly.
because as I
Instant.
move, it can see my motion.
Yeah.
So it's higher resolution thanks to gallium arsenide, and it's faster. Gallium nitride, sorry, and it's faster.
And it's faster, but it's less ambiguous. Because if you have a radar system, you need cameras to help you interpret what you're seeing.
Yeah.
With LiDAR, the only reason you need a camera is to tell red, yellow, green in a stoplight.
Okay. Yeah, because I can see this. This is I don't need any special processing. It's a 3D image. Yeah.
So you think about these massive processors that are being designed for autonomous vehicles.
I've never done an interview on LiDAR before.
Yeah, there you go. We're live on LiDAR.
We're live on LiDAR. Here's your colleague in the back setting up the LiDAR. There you go.
Yeah.
He's playing with it. That's on that laptop there.
And we're over here.
We're over.
Right
We're
there.
over in the corner.
Yeah.
Wow, that is so cool. That is really neat. What else can gallium nitride? Is there anything it can't do? What else can it do?
So my favorite, and gentlemen of age, pay attention here.
Yeah, I'm one of those. Yes.
Okay, this pill, which I promise is unused.
Do you have, Karsten, an over-the-shoulder shot here? So I'm a little worried about what it says. 3D colon imaging. Am I supposed to swallow that?
Well, that one you don't want to.
But
let's give you another one.
but the patient would, right?
The patient would.
And then inside, is that LiDAR? What is that?
Well, it's like LiDAR. It's actually an X-ray machine.
Inside here?
Yeah. And it's been hyper miniaturized using gallium nitride into a pill. And that X-ray machine is different than the other ones that you were talking about because those use optical cameras. And that's good for upper GI function because you
Right.
don't have a food in your upper GI.
Right.
But in your colon, you've got, we'll call it food.
Yes. Used food.
Yeah, well, processed. And for those gentlemen of age who have colonoscopies,
Right.
And if you haven't, you should.
Not a pleasant process.
And what's the unpleasant part is the pre-work.
Yeah,
that
because you have
do.
to clear out your colon so
Right.
that it can see.
Right,
It's because
'cause
it's a
they-
camera, and it's also, by the way, attached
To a stick.
To a stick, which does not enter through your mouth. That's all I'm going to say.
Right.
So this would be an alternative. Are people using this yet?
Yes, but
No
you
kidding.
don't need the preparation because the X-rays can tell the difference
Right.
between food and tissue.
It's true. The worst part of a colonoscopy is not the colonoscopy.
Yeah.
It's the prep for it the day before.
and in this case, it could be that the worst part is recovering the pill, but you don't have to do that either.
they don't put it in. They don't take it out. It's,
Marketing has taken care of all that. And
that's amazing.
But it
So-
wirelessly transmits to a patch you wear on your back. That's what you send into the doctor, and it gives you
Wait a minute. I
high
could use
resolution.
this at home,
Yeah.
and I put the patch on the back, swallow this. A day later, don't worry about it. It's going to pass through.
Yeah.
And then I send the patch, which has all the data.
Right.
That is amazing.
Right.
And that's because of the miniaturization capability.
And the genius of the people that,
Yeah,
that
no
developed
kidding.
it in
No
Israel.
kidding.
That's really the genius. It's being manufactured by GE Medical. It should be getting EC approval. That's European approval very soon, within weeks, months. And then 2019 for FDA approval in the U.S. It's gone through
Just in
its
time for my
clinical
next colonoscopy.
Exactly. I'm not having one until this is there. I'm waiting.
Doc, I'm waiting. Okay, so miniaturization is one of the benefits of gallium nitride. Speed is one of the benefits of gallium nitride.
Which leads to miniaturization.
Okay, they're linked.
Very much so, yeah.
Yeah. It's really what if you think about it, and I remember reading a wonderful book, which I tell everybody to read, called Microcosm by George Gilder.
Yeah, that was a great book.
The insight was that digital technology is different than anything we've ever invented because it gets faster and smaller and cheaper all at the same time.
The virtuous cycle. And that is very true of gallium nitride. The smaller you make it, the faster it gets, the cheaper it gets. And,
It's remarkable.
but we are right now, with our leading edge devices, we are 300 times away from the theoretical limit. Silicon is pretty much at that limit. So we are already several times better than silicon,
Yeah.
and lower cost. Imagine what happens when we get 300 times better than we are today.
Now you're making ICs, but not
digital ICs yet.
Not digital ICs. These are
Right.
analog ICs. At some point, could we see the next microprocessor in your computer on gallium nitride technology?
It's possible.
Is it suitable for that?
I'd say there are some technical hurdles that have to be overcome before it's really good for digital logic.
Okay.
I think they will be overcome, but it's not there yet. So
Okay.
in the meantime, we're working on all the analog and power functions, which is it's a small $75 billion market. I think we can work on that for a while.
Well, but this is how, as you pointed out, this is exactly how the progress happens.
Exactly.
It starts in these specialized areas, and that fuels further research, further growth, so you can get it into a more general purpose. So it sounds like, I imagine, in a decade or whatever it takes, we will see computers could even be 10 times faster. Is that, do you think, the possibility?
Or 100 or
Or
1,000
more.
times faster, yeah. Yeah.
Wow.
I don't know what we would do with it, but then again, I said that 10 years ago.
Me too. Yeah. No one will ever need more than 640 kilobytes of memory. Well, this is very interesting. We're talking to Alex Lido. He is the founder and CEO of a company called EPC, Efficient Power Conversion, based on this, research that he and others have done over the last couple of decades, and the creation of a new technology for creating processors, transistors, and ICs called gallium nitride. We're going to take a break, and during the break, we're going to move over to the other side of the set, because we have a number of products that use gallium nitride that you probably will recognize. Things already in your daily life. We'll have more with Alex and Triangulation in just a second. Hope you're having fun learning more about, as I am learning too, about gallium nitride technology. We thank our guest, and we've got lots more to come and some pretty cool demos. But first, let me talk about ZipRecruiter. If you're the hiring person at your company, you know that is a job, well, it's a thankless task. First of all, if it's a small company like ours, you're doing it while you're already down somebody, right? So you're working harder anyway. Plus, how do you find that perfect employee? Your company is made of people. A good employee can transform your company. A bad employee can bring it down. And nobody wants to hire the wrong person. Hire the right person fast. That person is out there. You just have to know how to get to them, and that's why I love ZipRecruiter. Because with one posting, it's very easy for you. You get to 100+ job boards with one click, and Facebook and Twitter. Yeah, your posting's everywhere. It's going to reach the largest number of people in any industry, anywhere in the country. And that's important because you don't know where that perfect person is. This way, everybody gets to see him. Now, you say, I know what you're saying, because I said this too. Oh, but that means I'm going to get, 1 million resumes in my email, or people are going to be calling me? No, because ZipRecruiter has all of those applicants roll into the ZipRecruiter interface. They format the resumes so they're all the same, easy to read. You give them screening questions. They give you a chance to say yes, no questions, or essay questions, or multiple choice. So you could just say, no, I don't want that person. I don't want that person. You can eliminate all the bad ones. And their smart matching technology is unique. There's no one in the business that does this. It will notify. It's like a push to qualified candidates. So they know what you're looking for. They will push out to qualified candidates about your job within minutes of posting. That's why 80% of employers who post on ZipRecruiter get qualified candidates in as little as 1 day. Unlike other hiring sites, ZipRecruiter doesn't depend on the right candidates finding you. It finds them. And it's so easy to screen them, rank them, and hire the right person fast. Once you do this, you will never go to any other system. No wonder 1 million businesses of all sizes use ZipRecruiter, some of the biggest, most important businesses in the country, and some little ones like us. We use them. Find out today why ZipRecruiter has been used by everybody to find the most qualified job candidates with immediate results. ZipRecruiter, it's simple, is the smartest way to hire. And right now you can post jobs on ZipRecruiter free. Free. Go to ZipRecruiter.com/twit. ZipRecruiter.com/twit. We thank them so much for their support of triangulation. Let's get back to our friend gallium nitride. Welcome back to Triangulation. My guest, Alex Lido, is still here, but we've moved over because we wanted to show some stuff that gallium nitride can do, gallium nitride technologies. Alex is the CEO and founder of a company called Efficient Power Conversion, EPC, that is built around making gallium nitride chips available in FETs, field effect transistors, and ICs, but used mostly for, I gather from the name, mostly for power.
Yeah, power and analog.
Okay, so every one of these things is using it in some way.
Right.
What is this? Is this a motherboard? What is this over here?
So this is just a little antenna. And
that's an antenna.
Imagine
Okay.
for a moment a small solar panel and a battery pack on this thing, and along comes a drone that's delivering your pizza, and it's running out of fuel. Just comes along here, and in midair.
Wait a minute. It's getting power from that?
In midair. We don't have it flying because they wouldn't let us do it.
Okay, now I have to admit that I have been poo-pooing the notion of wireless charging at a distance. I thought the physics don't work. It can't be done. Boy, was I wrong. I mean, that's about, what, 4 inches, 5 inches?
You can make it 5 feet if you want.
You cannot, because don't you have to send so much power that you'll fry anything in the
So here's
in
the
between?
trick. Here's the trick.
Yeah.
This is for outdoor use.
Okay.
Yeah,
you don't
'cause
want it in your house.
You don't want it indoors. But we'll get to the indoors in a minute.
But if I were to stick my hand in there, would that be dangerous? Okay.
it'll stop it.
Oh,
If
because
it's
we're
enough
big
power,
bags of water.
it could be dangerous.
Yeah.
But at
How
this
much
low
power is that? How much charging is that able to do?
Well, this could do 10 kilowatts if you wanted to.
That's huge.
Yeah, I mean, it'd be a little bit bigger antenna. But it could
Something
do as
like
much
this
as
is
you want.
probably really only needing 10 watts or
10
less.
or 15 watts, yeah. But it transmits at a very high frequency,
So wait-
so silicon can't do it.
My mind is boggled. So what is? You said it was an antenna.
Yeah.
It's not really an antenna. What is it?
Well, it is. It is an antenna. It's sending out these waves. And
It's a
these are
transmitter, not an antenna. It's not receiving. It's sending.
It's sending unit. Yeah.
It's sending what?
It's sending
Is it a microwave?
frequency at 13.56 megahertz, which is
Oh, it's not. That's not high frequency. That's relatively low. That's FM band kind.
Yeah.
Yeah.
But it's a lot of power, and that means it takes a higher power device like gallium nitride. And then you can see the bottom of this has got some receivers on it.
It's
Copper.
Copper. It's
Yeah.
conductor. So so is it inductance? How is it charging?
It's just receiving electromagnetic waves.
It's just getting
It's
power.
not inductance.
It's like plugging it in.
It's like picking up your FM radio signal, except at a higher power level, which is okay for outdoor use, not for indoor use.
I know, we have here in San Francisco Bay Area a radio tower, Sutro Tower, beautiful tower. It's got the best view of the San Francisco Bay.
Mm-hmm.
But and I've been up there, but if you go up there, you're supposed to wear a metal mesh bunny suit.
Yeah.
It's FM, but it's so high power FM, it's 100,000 watts, that you could, and in fact, when we went up there, but once it was before bunny suits, I got RF burns, little white dots all over my, that's not good.
That's not good.
That's not good. But you're not, so this isn't going to be in the house.
No, but think of it, this is an inexpensive thing. You could throw out the back of an airplane and make a path up to the North Pole where you could now send, critical metal supply, or medical supplies or whatever,
Wow.
or have these on rooftops and deliver your pizza or your packages.
Do you have to get FCC approval for something like that? I think you would, wouldn't
Today,
you?
no, because it's actually an unlicensed scientific and medical band called ISM band.
Okay.
And 13.56 megahertz.
So nothing's there.
Nothing's
it
there.
is just
It's an
below
open
the FM frequency.
but you got to stay right in that slot.
It's kind of like 2.4 gigahertz was as an unregulated band. It meant people,
Right.
that's where innovation happened.
Yeah.
So tell me, so where is the gallium nitride in that?
It's right in this little circuit. You can't even see back here. There's two tiny little blue dots. See how tiny those are?
Yeah, I
And
can't
those are
actually see them.
Yeah,
That's
they're
how
tiny little blue things there.
Okay.
And
Burke, can you see those? Burke, focus, zoom, enhance, center. Yeah, you can't see them.
that. You can try.
You can't see. So that's a transformer or a step-down transformer.
Well, this actually is it generates a lot of power at 13.56 megahertz. It's an amplifier. like
Got
a
it.
power amplifier. You have tiny ones in your cell phone,
Okay. Those could use gallium nitride too. Then.
and they will. As a matter of fact, if
interesting.
you look at the base stations, they use gallium nitride today.
Really?
Yeah.
Okay.
And 5G, it's critical to use gallium nitride.
So just to reiterate, the reason this is a breakthrough is that the new semiconductor that's on silicon still, but it's on top of silicon, is so efficient that you can switch at a much higher rate, much faster, right? And the faster switching means that you can do the step down, the voltage step down that you need to do in a smaller unit. One step also.
In this case, it's different because you're talking about a power supply.
Yeah.
It goes from high to low or sometimes low to high.
Yeah.
This is actually an amplifier. And if you look at the amplifiers in your cell phone, they're maybe 30, 40% efficient.
Right.
If you look at this is 90-something% efficient. And if you're conducting a lot of power, you kind of care about efficiency.
Right.
So the gallium
So this is an
nitride,
IC, an FET. This is a transistor.
These actually use discrete transistors or
Okay.
FETs. Yeah.
Okay.
And I think, you know, for package delivery,
No,
is
this makes a
solution.
lot. This is a very practical and very interesting solution.
Yeah.
But it is kind of the goal, the dream of everybody at home to have power charging at distance. That seems to me difficult because you're going to have to send a lot of power through the air.
Right. So I think that it's kind of a step at a time.
Right.
And for now, the issue is get it on a two-dimensional plane.
Right.
In this case, you get 3 dimensions, but outdoors.
Right.
But if you look at this just came out a couple weeks
This
ago.
is a new Dell laptop.
Yeah. The 7285
Okay.
Inspiron.
I like it. It's really small. It's beautiful.
Yeah.
But watch.
So if
It doesn't have a power supply.
Yeah, there's no power cord to it. And you see it goes dim because the power is off, and I think if you put it
have
on
to
here,
turn it-
it'll
turn it back on.
It'll turn back on. But it's powered through this
Yeah, there it is.
charging pad.
So it's not plugged in.
Right.
And is this similar to what the
So it's
drone was
different.
using? Okay.
And it's critical difference because this uses only magnetic field. And it uses something
So
called
this is now inductance charging.
it's resonant magnetic. It actually, like the Earth has these magnetic fields around it.
Yeah.
Well, it taps into those magnetic fields at a distance, and since it's resonating, those magnetic fields transfer a little bit of energy each resonant cycle.
Right.
And it can power a lot of things. And it's safe because we don't absorb magnetic waves.
Right. We don't have
So-
any iron in our body.
Yes, that's correct. So you have a safety factor behind this kind of magnetic
That's
resonance.
fascinating.
Yeah.
It's, as opposed to an inductance charger, which is the wireless charger we're using in most
Right.
devices today.
Like an electric toothbrush has an inductive
Yeah, you
charge.
put it on there. So you're gonna have to explain this because I'm a dummy when it comes to analog. Inductance charging, I kind of understand because you're creating an electric field and you've got coils and it generates electricity. It's almost like it's turning something to generate electricity, but it's turning magnetic field to generate it, right?
Right.
How does this work? How is that? I don't understand how this kind of charging works.
So it generates just like around the Earth.
I understand okay, but it has its. So in effect, this is like the magnetic poles on the Earth, but it's generated by this pad.
Tiny little poles.
Tiny little poles. And then what is the reaction that's happening with this?
So in here, there's an antenna,
an antenna.
and it receives those things, but they all resonate at the same frequency. In this
Yeah.
case, 6.78 megahertz,
Yeah.
which is also an ISM band, so it's unlicensed.
Nice. Okay.
And is also too fast for
So there's
silicon.
RF coming off of this.
That's not really RF in that frequency,
Oh, okay.
and it's magnetic field only.
Okay.
So you have no EMI, no
it.
electromagnetic
Got it.
radiation.
Got it.
And by resonating, you can tap into that magnetic field a little bit at a time.
You get little microcharges each time.
And then you can reassemble that
Wow.
into a big charge.
Wow. So where's the gallium nitride in that?
Well, the gallium nitride's in the transmitter.
Okay.
And
Not in the receiver, though.
not in the receiver, but it's going into receivers all over the place. I'll show you in
I
a
would
minute.
think there'd be a benefit to that.
Yeah.
All right.
So there's that, and
That's cool.
This is a really cool computer, and but you see it has a charging pad.
Yeah, this is the negative, though. I mean, I'd actually prefer to carry a charging brick
Yeah.
along than this. So can we do better?
We can do better.
We're
And
gonna
funny
skip.
that you asked.
We showed you before the LiDAR. So this is the LiDAR that we had mentioned and we
Right.
showed on the
Exactly.
screen before. And this is, again, made possible at a much lower cost thanks to gallium nitride.
Well, it's made possible at all because with silicon, the image is very fuzzy and
Just
very slow.
useless.
So
Yeah,
it's
yeah.
not as useful as radar.
That's so cool. But if we come over here, this. So what are we looking at here? This is weird. Watch this.
Whole table.
Watch this. So this light, I'll shine it in your eyes, is on. If I lift it up, this
Look at the
lamp is
bottom.
getting powered by the table.
Yeah, but you see the little antenna in there to receive it?
Same technology
Same technology
as with the Dell laptop.
with the Dell laptop. Yeah.
So this table is putting off a completely harmless mini magnetic field like the Earth's core.
Yeah, and same with this this computer. We put our own antenna in here.
Ah.
See?
I like that. I don't mind carrying around but this is the table is what's charging it.
Right, so you don't have to worry where you put it. You just put it down and it'll turn on or it'll
Don't you
charge.
want that in your house? A phone, here's a blue phone that's being charged. And again, it's not the antenna is small.
Yeah.
It's not a big deal to put in there.
It's like a piece of like a calling card in there.
See, I remember doing this to take a Samsung Galaxy Note that didn't have wireless charging. You'd buy a little thing that would have pins on the back and put it in. But that was an inductive charging.
Right, and
pad.
you had to find a target somewhere to set it
Yeah,
on,
in fact,
right?
that's one of the biggest problems with wireless charging right now is you got to get it just right so that it creates a field so that it'll charge. This doesn't have that problem?
No, it's anywhere on the table. And, you know, you can think of a conference room or a desktop. Here we have, you see it's charging now.
Look at that. That's amazing.
We have one of these
This is an Echo
Echoes.
Dot, yep.
If you wait a minute, it'll boot itself up and start talking at us.
And that's, of course, not built into the dot, but this is that pad below it.
Yeah.
Although there's no reason, look, it's going on.
See, there's
no
antenna.
reason Amazon couldn't put that in the bottom of a dot, right? It's
And
not
it-
a big,
it
it's not really
costs
this thick.
Nothing.
Yeah.
You know, if you look at it, we're saving all these power cords.
These are all
Look
the
at that.
cords they brought, but
That's
don't
what
need.
we say.
I love this. There's a Google Home.
Because we have to
same
be
thing.
agnostic.
Yeah, yeah. And so if I pick this up, yep, the light goes out.
Yeah.
But I put it back on, it starts immediately.
Right.
So how many watts can this Surface generate?
So this one is tuned for about 180 watts.
Well, that's a lot.
Yeah.
Yeah.
But it could be anything.
So that would limit the number of devices you could put on here.
Right. But that was just
That's
our
still a
decision
lot.
to make it so that it powered all these things without
Right.
a problem. See, the monitor there, that also is wirelessly powered. Yeah. Just pull it up and it'll go off, and then you can put it back down and it'll
No,
go back
I don't
on.
believe it. Look at that. Look at that. And there goes the Google Home just started up. I heard the magic tone. Look at that. So this could be your desk.
That's, yeah, exactly. And think
love
about it
that
also as it could be your kitchen counter.
Yeah,
And, you know, kitchens have a lot of water around.
right.
So if you could put your toaster, your blender, your KitchenAid mixer, all those things, just set them down and they're powered.
Nice.
That's the way to do it.
Is this going to be a product?
We believe so. We're talking to several people about making it into a product.
Neat.
And probably one of the first things will be nightstands.
Look at the Amazon Echo just started up. It'd be great for a nightstand.
Yeah.
See, right now I love wireless. I think we all love wireless charging for our phones. But as you point out exactly, you got to aim it. You got to get it in just right. This is so much easier. I'd love this on a nightstand. And again, it's harmless to humans.
Harmless to humans because we don't absorb magnetism.
Right.
So
Right.
it doesn't make any difference to that. And the magnetic field goes about an inch above the table and stops at the edges
Okay.
anyway.
Okay.
So you can't really interfere with anything off to the left or the right if there were an issue with
Interesting. And it's a weak enough field that I don't feel it. It's not pulling
Right.
on me or anything. If I had wow, that is really that is very exciting. Is it expensive to do this? Is this going to be?
that. So when we converted the monitor over there, we actually were able to take out all the AC equipment, you know,
Right.
the AC converter, and
Yep.
put our stuff in. Cost is about neutral.
About the same.
Yeah.
So this is something really to be. If you had, so I can imagine somebody selling a power desk or a power table.
Power desk. That sounds good.
I like the power desk. I'm probably copyright by somebody else. Somebody else's trademark. But I could really see the advantage of having something like that.
We also have a flat screen TV, a big flat screen TV that you stick on the wall and it turns on.
Sure, if you could do 180 watts, there's pretty much nothing you can
Right.
power with that. That's
So
pretty
imagine
impressive.
in your house today, if you have a flat screen TV, It already receives all the signals wirelessly.
The real problem is that plug. Yeah.
Yeah, it's the only thing left.
Put it on the wall.
Now, you come from a marketing background, so
Them's fighting words.
So I challenge a marketing guy to find somebody who likes power cords.
Nobody
likes them. So why the heck do we still have them?
I love it. I was in marketing for 3 months, okay? And I was young. I needed the money. I had nothing to do with it. And ever since I've avoided it like that. No, now why is it changing as I move it through the field?
Oh, because there's actually because of the
There's a
original
bump here?
design. There's a little dead spot there and a
Got
little
it.
dead spot there, but
Doesn't have to be.
That's just the Mark I version.
Right. Now, and we should emphasize that EPC doesn't make any of these
End products.
consumer end products, but you make the gallium nitride devices, the FETs and the ICs that make these things possible.
Exactly.
Very, very exciting. Well, I wish you all the best. I think it's a really amazing technology.
Thank you.
Yeah. And at some point, you think Intel and others will start building fabs that support gallium nitride?
Well, today we build gallium nitride in a standard silicon foundry. That's,
Oh, you don't need to build a new factory?
Don't need to build a new factory. You just put it in with silicon and it runs just fine. You have to have a special machine to grow the initial crystal on top of silicon, but that's a very small step. And then you put it in there and it's
You do that in a
standard
shed out back and then do the rest
Right.
and be the same factory.
Yeah.
Very interesting. I know a fruit company that'd be very interested in some sort of wireless charging technology like that.
I
But
hope so.
I won't say anything. I won't ask. Alex Lito, thank you so much for joining us. Alex is the founder and CEO of EPC Efficient Power Conversion. You make the gallium nitride FETs, field effect transistors, and ICs that power these products and could actually change a lot of how we get powered. That's exciting.
Absolutely. Thanks so much,
that's
Leo. It was
really
great
nice
fun.
to meet you. We do triangulation every Monday, 11 a.m. Pacific, 2 p.m. Eastern Time. If you want to stop by and say hi, join us in the chat room at irc.twit.tv. You can watch the live feed on our website, twit.tv/live, on YouTube Live, Ustream, Twitch. We're everywhere. But if you can't be here live and join us as the third leg of the triangulation stool, the third side of the isosceles triangle, actually it's more like an equilateral triangle, then you can always come by and download the show at twit.tv/TRI. That's our website. But the best way, frankly, subscribe. Find your favorite podcast application and subscribe to Triangulation, because I tell you what, you're going to want every week. And you're going to collect them. Collect the whole set. Thanks for being here. And we'll see you next time on Triangulation. Bye-bye.